Hello, Physics 20s. I'd like to take a minute on the introductory notes for circular motion today. Uh, Circular motion has its foundation built upon uniform motion. So the very first formula we ever learned, which was velocity equals distance divided by time, here it is right there. We are going to show you how circular motion is based upon that. But to do that, we need to look at a couple other definitions here. So um, if an object's moving in a circle, we call that uniform circular motion. It just means that you're moving in circular motion at a constant speed. Okay, so the tangential speed, or the speed that's perpendicular to the curvature of the line, stays the same. It's not bad to note the axis of rotation. That's just the very center through which everything is going around. The tangent line, or sometimes, I guess I could have added that. Sometimes I call that the tangential. Okay, a tangential line. Okay, if that makes sense. So that is actually this line right here. So if you see it down here, it's a line that is drawn perpendicular to the curvature of the circle. Okay, and basically that just means this this straight line that I drew there, it just touches the circle at one point, and it's perpendicular to the curvature. Okay, so the radial line, in that case, we don't deal with radial lines too much because we tend to deal with degrees. But a radial line are like the spokes on a tire that come outwards from the very center. So you'd have radial lines that would go out like this. Okay, so let's get down to the formula though for circular motion. We are only going to largely deal with speed in a circle that's constant. And so what we do is we have to consider the distance that the object travels and then how much time elapses. So instead of using d, we use 2 pi r, because we are going to consider, the easiest way to measure circular motion is to consider one complete circle. Okay, so if you start at one point in a circle and go all the way around, you will have gone through the diameter, or sorry, you would have gone through the circumference of that circle. Now, very quickly here, we're going to be dealing with a unit of measurement called the period. And the time for one rotation is called the period, and it's labeled with a capital T. There it is right there. And we call that the period. And all that, that term is defined down below, but the period is the time that it takes to go all the way around once. So if you were mapping how much time it takes to go around a circle, okay, so from one point to where it comes back to that point, that would be the period. Okay, and we use that time as a special designated time instead of little t. And then boom, we have a new formula, which is right there. Okay, velocity, and I guess we start using the subscript c. So that means centripetal. No, actually, I haven't defined that yet either, or circular if it helps you. Vc equals 2 pi r, which is the diameter, or the circumference, sorry, of the circle, divided by the period. So this brings up a misconception that's kind of fun to talk about when we're studying circular motion. And it kind of defines it down here. We talk about, in physics, we talk about the centripetal force. Okay, centripetal means center seeking. And the term that I'm sure you've heard of is the term centrifugal, F-U-G-A-L. Okay, that means center leaving. And the misconception is, and it's a pretty easy one to understand, is that most people imagine if something's moving in a circle that that you're experiencing a centrifugal force, that there's a force that's trying to pull you away from the center. Now, if we come back to this circle here, and I was talking about something going in a circle. If you're moving around in a circle, and then all of a sudden, let's say you're being held by a string, just like I'm showing here. So there's something on a string, and you're just spinning it in a circle. If at a certain point you cut that string, let's say we cut the string right there, okay? As you can see, the velocity, or the centripetal velocity, as we say, is tangential or perpendicular to the curve. And so if you were to cut the string right there, then the object would not immediately go outwards, as I'm showing with this dotted line. The object would continue to move in the direction it's already moving, basically due to Newton's first law, that if there's no force acting on an object, then it'll just, due to the law of inertia, it'll just keep doing what it's doing. And so in that case, it means that the object will continue in that direction. So it actually doesn't move away from the circle. It does not do that. It is moving away from the circle, but it's not directly away. It's actually tangential or perpendicular to the curvature. And so that there is the slight misconception worth mentioning, that, and for that reason, we won't use the word centrifugal. I'm not going to use that word, or you won't see it defined that way. Because as an object is moving in a circle around, or as an object is moving in a circle, the force is always directed towards the center, as I'm trying to show you right here. Okay? The force is always directed towards the center. And so the force then is known as a centripetal force. Okay? So maybe just kind of clear some of that off. A couple other terms. I guess we should mention cycle. That's going to come up a bit later. A cycle is just a complete back and forth motion. We're dealing with a revolution here. So when things are moving in a circle, they'll go all the way around in one complete cycle. There's the term period, which we already defined. It's the time for one complete cycle. But period has an interesting relative, and that is frequency. Frequency is the number of cycles per unit of time. And as we note down here, we measure frequency of an object in cycles per second. Okay? There's a special term for that, as noted right beside it, and that is hertz. Frequency, and that frequency is lowercase f, okay? And it's measured in cycles. I guess I didn't write that in here. It's really the number of cycles per second, or hertz. Hertz is named after Heinrich Hertz. He did some really cool experiments with AC waves, alternating current waves, and he was measuring their frequency in cycles. So in honor of him, eventually that was adopted. So you'll see that you'll see the units Hz for frequency. Okay. Now, most of you are also familiar with frequency in terms of rotations per minute, or RPM. Okay. So if you, the tachometers on your motorcycle or on your vehicle, if you happen to have one, they tend to measure the rotations per minute. That's helpful sometimes, but if you ever see rotations per minute, you need to switch that and get it into rotations per second, or RPS, which is the same as hertz. Okay, so rotations per second is the same as cycles per second, which is hertz. So just be prepared for that. You most of the time deal with frequency, though, in cycles per second. So we've already defined period, and there it is there. But here's the cool relationship. This is one of the formulas on your formula sheet. period is equal to 1 divided by the frequency. And vice versa. That's why I say they're relatives. Frequency is equal to 1 divided by the period. So they are reciprocals of each other. And you can maybe see that instead of having cycles per second, if you reciprocate that fraction, now it becomes seconds per cycle. And that's exactly how these guys are related. So be prepared for that. You'll see a couple of those practice questions coming up. Now, what I really should say here is that back up here, this is velocity centripetal, or we could say this is centripetal velocity. As soon as we have a new formula for velocity, that opens up a whole bunch of cascading formulas. Because if we know a velocity, then we can find an acceleration. And if we know an acceleration, then we could find a force. Because force is equal to mass times acceleration. We've already done that in chapter 3. And so I want to just show you how all these formulas are related, because very quickly here, I'm going to ask you to do some practice questions with each of them. Okay, so let's deal with centripetal acceleration first. And I'm just going to get, you just need to trust me on this. If you've seen the video, it actually shows how the direction of the velocity, the change in velocity, is always directed towards the center of the circle, especially for an object that's moving in a circle. So even though the centripetal velocity is staying the same as you go around and around in a circle, because you're changing direction the whole time, every second you keep changing direction. If you're changing your direction, that means technically that you are accelerating, and you definitely are. So one of the formulas that you don't need to know how to derive it at this point, but for centripetal acceleration, I guess that should have an arrow on it, but that's okay, is the velocity centripetal squared divided by the radius. And if this is the most standard variation, but we can actually plug in the formula for centripetal velocity, which is 2 pi r over t. If we stick that into here, basically it just means we have to square it. So if we square that and recognize that that's being divided by the radius still, then basically you're going to get, and I guess I could write it temporarily over here, you're going to get 4 pi squared r squared over t squared over r. Okay? Now don't forget that over r, because that's what this r is right there. Okay, that r is down here. So, but as some of you can maybe tell, this is actually the formula for centripetal acceleration also, but we can simplify it because that r at the bottom will cancel out one of the r's on the top, and then you get 4 pi squared r over t squared, which is that formula as well. So you have two formulas for centripetal acceleration, and just be really slow as you learn these, because you could use either one. Okay, so if you're given the period and you know the radius, you could find the centripetal acceleration. Or maybe you weren't given the period, but you were given the velocity. So if you're given the velocity, then you square that velocity and divide it by the radius, and then you can get centripetal acceleration. Okay. Now, that leads us to the last new formula in circular motion, and these are all tied together. Now, there's more coming, but these are the first main ones because we deal with these in a pile of applications. So, if the object is accelerating, then if we multiply it by its mass, we can get the force. And in this case, we are getting what's called centripetal force. So this would be the force that's directed towards the center of the circle. If you're, swinging a pail of water over your head, that's kind of a fun example too. Or, and as well, we're eventually going to get into orbits as objects are being pulled into a circular motion by the force of gravity. So anyway, you might note that this could also be at the centripetal force will equal the mass of the object times the centripetal acceleration, AC, okay, which is what it there. So, but AC, as we know, we just learned that there's two formulas for that, okay, that one and that one. And so if we just substitute those in for acceleration, then you get two more formulas, okay? So I know I went through that very quickly, but I just want you to be comfortable with this section. It's all on the back of your formula sheet near the top. And to give you some practice with all of those, I'm going to let you do these practice questions. And I'll maybe just do the very first one with you. And I will post the answers to these shortly. But I'd like you to just carefully go through all three. They're going to add you, if you know you're dealing with period or frequency, you've got the formula for that. If you're dealing with circular or centripetal velocity, you have the formula for that, centripetal acceleration or centripetal force, okay? So all of those are all tied together. So a standard grasp method here on this first one, if you're going to calculate the centripetal force, that would be Fc. And we have the mass of the object. We have the speed that it says whirling at a speed, so it looks like that's the speed in a circle, and it has a radius of 0.6. So if you're trying to solve for centripetal force, I'm hoping you'll see quite straightforwardly that this is going to be mv squared over r, okay? And with 1.5 kilograms and 2.3 meters per second. Now, the crucial step is, of course, you have to square the velocity. That's an easy miss when students are first learning it, so just pay attention there. But then you're dividing by 0.6. This actually will come out to 13.225 newtons. It looks like we have to round it to two significant digits, so it looks like it's 13 newtons. And I would add it's towards the center. Okay, so there's some really cool applications of circular motion, and I'll try and get to some of those soon, but you may have already seen those in some of the videos. So off you go.